Hello friends, in this lesson we'll learn about metal containers or packaging material made from metals. In this we will be discussing about the history of metal containers, how they were developed, then the design and configurations, their merits and demerits, and their application in the food packaging industry. The commercial packaging of foods in metal containers began in the early 19th century, following on from the discovery in the 1790s by the French confectioner Nicolas Appert of a method of conserving all kinds of food substances in containers, a method to which the term canning is now applied indiscriminately, whether the container is made from tin plate, aluminium, glass, or plastic. The earliest can makers were tinsmiths who turned out tin plate containers with skill and imagination in a variety of sizes and shapes. Both ends were soldered to the body with a hole about 25 mm in diameter at the top. After can was filled through this hole, a metal disc was soldered into the place. Mechanization of the can making process was made possible by the development of a method called double seaming to attach ends to the soldered can body. Even though many of the fundamental manufacturing processes such as double seaming and body forming were developed in the late 19th century, the evolution of can making continues. Related technologies such as metallurgy and food engineering are also advancing, creating new applications for the metal packaging materials. Of the total estimated world market of metal cans, about 78% is accounted for drink cans and about 18% for the processed food products. The remainder are aerosol and general line cans. Drink cans may be divided into those for non-carbonated drinks like coffee, tea, sports drinks, etc. and carbonated beverages like soft drinks, many of which pass through a pasteurization process. The metal packages for food products must perform the following basic functions if the contents are to be delivered to the ultimate consumer in a safe and wholesome manner. First one is to preserve and protect the product. The next is resist the chemical actions of product, withstand the handling and processing conditions, withstand the external environment conditions, mainly during the transportation. The next one is to have a correct dimensions and the ability to be practically interchangeable with similar products from other supply sources whenever it is necessary. And it should have the required shelf display properties at the point of sale. This is very important property because the customer would see the package when first he or she will be seeing it, he or she will be going to attract towards it. So this is very important property. The next property is to provide easy opening and simple product removal. This is also important because handling should be very easy for any packaged food product, and it should be constructed from recyclable raw materials. Most filled food and drink containers for ambient self-storage are subjected to some form of heat process to increase the shelf life of the product. The heat process cycles used to achieve this are particularly severe, and containers must be designed so as to withstand these conditions of temperature and pressure cycles in a steam and or water atmospheres. After heat processing, when the can temperature has returned to ambient, there will be normally be a negative pressure in the can, or we can say that it will be under vacuum. Under these conditions, the food product itself does not provide any strength to the can to resist the external loads. But vis-a-vis in case of carbonated beverages or carbonated beverage cans, which form the bulk of drink cans filled, once the container is closed, the carbonation pressure continues to provide significant physical support to the container until the moment of opening. In the case of still liquids such as juices, nitrogen gas may be used to provide the necessary internal pressure for rigidity and compression strength. The internal pressure is required to have a proper strength and also to decrease the gauge of the metal cans used for the such kind of beverages. When we see the merits and demerits of metal containers, first of all we will see the merits. They are very good, attractive, and they are having very good bearing properties, or they are good barrier to moisture, light, and even gases. The demerits, if we compare, then the cost of production line is high, and even the cost of the material itself is high if it is not recyclable. But normally the most of the cans or the metal material are recyclable, so the cost will increase only of the production line, and even the cost can be increased because of the different sizes and packs to be manufactured, and for that sometimes different processing lines are to be utilized. Now we will discuss about container designs. Regardless of the particular can forming process used, the shape of metal containers are very relevant to their cost, physical performance, and compatibility with the field product. For most metal food and drink containers, the cost of metal itself is 50 to 70% of the total container cost. The amount of metal in any particular container is the most significant cost item, and this is related to the metal thickness, temper, and its surface area. In can design, metal thickness is determined by the need of physical performance in handling, processing, and storage of filled containers. Surface area is determined by volume contents and the shape of the container. For ease of manufacture and handling, most food and drink cans have a circular cross section, but for different physical performance, cost, and product uses, cans may vary from shallow to tall. This depends on the size and the type of product to be filled. Now discussing about can configurations, there are three basic types of cans: 3-piece cans, 2-piece drawn and iron cans, and 2-piece drawn and redrawn cans. 3-piece cans, as the name suggests, it is made in 3 pieces, a body and 2 ends. The manufacture of 3-piece cans involves the cutting of metal sheet into can width strips on a machine called slitter. The slit strips are cut into body blanks and fed into body maker, the first machine in an automatic can line. In the body maker, the body blanks are rolled, the corners are notched to remove the extra thickness, and the side seam is curled into the ends and passed on to side seamers. Within 3-piece category cans, there are 3 further classifications determined by the method used to join the side seam of the body cylinder. The methods are soldering, welding, and cementing. So in the first one is soldered seam. For soldered cans, the edges of blanks are bent, brushed with flux, passed over a gas flame, and joined in a lap and lock system while moving over solder application seam. Another burner smoothens the seam and wiper removes excess solder. The soldering seam is then treated with a lacquer. The body blank is flanged to receive the can bottom, which is double seam. The top of the can is usually applied after a filling operation. In the final step, spray coating is applied to the can interior, cured and tested for leaks. Another one is welded seams. The welded side seams are very strong and require much narrower under coated strip than that needed for soldering. In welding, the side seam is an overwrap of cured plate which is subjected to a high amperage electric current in a resistance welding process. The resulting exposed edge inside the can is coated in a stripping operation using powder coating which is cured by infrared or high frequency induction heating. And the last process which is used is a cemented seams or cemented seaming. The cemented side seams permit all-round lithography with no base strip required at the solder point. The body former curves the sheet to form a cylinder and overlaps the edges. Cemented seams are produced by passing the body blank edges over an open flame and applying special cement with wheel. Chilling rolls then solidify the cement, and trimming knives remove the excess cement between the adjacent body blanks. The exposed edges are coated with lacquer. A thorough test is to be followed before cemented side seams are used for can under pressure, because there is a chances of leakage if the cement is not applied properly. Then the next type of cans are two-piece drawn and iron cans. These cans were developed in 1960s. This method of can manufacturing eradicates the side seam and separate bottom. It combines the seam and bottom, or the body and the bottom. The two-piece can body has an integral side and bottom and is made in a process that thins the side wall while maintaining the thickness of the bottom. The widest use of this is in the beer and soft drink markets. To make a D&I or drawn and iron cans, a disc of metal sheet is formed into shallow cup with a die. The cup is then pushed through several dies, each slightly smaller than the previous one, so that the side walls are stretched and thinned. Since the cup is held on the original punch, the inside dimension remains constant during this process. Starting with the plate thickness of 292 micrometers, the side walls are reduced to 97 micrometers, while the bottom thickness remains the same. This process of pushing the cup to progressively smaller die is termed as ironing of side wall. As the walls are ironed, the bottom is domed to provide strength and stability. The maximum ratio of height to diameter which is allowed is 2:1. The can bodies are then cut to length and cleaned in preparation for coating inside and out. The can is then necked at the top and flanged to receive a top. The necking is produced a can with a narrower top, thereby saving the material. After leak test, the cans are generally prepared for filling of the beverage. The next method is two-piece drawn and redrawn cans. In this method, the cup is pushed through each succeeding die. The gauge of the bottom and the side wall of container remains essentially the same as the starting gauge, but the inner dimension of the cup becomes smaller. One or more punching operation may be used depending upon the depth of the can to be produced. These subsequent drawings or redrawings can be done once or twice. After drawing and redrawing, the can body is necked in at the bottom to permit easy stacking and incrusted in narrow bands to provide extra side wall strength for vacuum packaging. While coating will not adhere to D and I cans during production and must be applied to after the can body is formed. They may be applied to the flat can stock in D and R process prior to the drawing. A typical can, for example fruits and vegetable, would start with still having 184.6 micrometer gauge and ends up with a side wall of 179.5 micrometer. The maximum ratio of height to diameter allowed is about 1.5:1. Now we will discuss about the non-round cross-section containers. They are typically used for fish and meats that are heat processed, as well as for products such as edible oils which do not need to be processed. Open trays of round or non-round sections are used for baked food products, or with lids are generally used for takeaway food containers. Now we will see the different closure systems for metal type of containers. The closure systems for food and drink cans are by necessity very different in their mode of operation. Food cans require an aperture with either total or virtually full internal diameter of the container through which to remove the product, whereas the aperture for drink cans is designed to suit the method of consumption, or we can directly consume the product from the can. Historically, food cans have required a can opening tool to remove the plain lid. In more recent years, full aperture easy open ends have been developed based on designs originally used for drink products. Whether plain or easy open ends are used, the end panel for virtually all food and drink cans is mechanically seamed on to produce a double seam that is capable of withstanding all the heat processing cycles used. So in this, first one is easy open ends. Easy open ends could be stay on tap found on the beverage cans, or a ring pull ends which is found on pet food or a heat sealable flexible membrane. The beverage can end is a tabless design with a raised conical profile and a central 19.1 mm pour spout. It is opened by pressing downward a circular panel which pops inward without leaving any hazardous edges. The recent advancement in the easy open membrane lids, which simply peel away and often are teamed with a fraction of fit plastic lid. Then the next type of closure is a threaded closure. Screw top cans are containers which are generally used with this type of closures. A wide variety of threaded spouts and applicators have been available. A closure could be specified by size of outside of the threads on the container. There are no industry standards for threaded profiles. The caps from the one manufacturer may not fit the containers from the another. So the caps and containers must be purchased at the same time from the same source to ensure a good fit. Then the next category is slip cover closures. Shallow cans with slip covers are made by blanking and drawing metal plate to the proper size and curling the edge. This category of closures includes simple recloser type, firm recloser type, or friction closer type. There are still markets for highly decorated metal boxes. Although the uses of these slip cover containers have greatly decreased due to the labor intensive cost of making these cans, has sword and other types of mass produced containers have developed. Now we will discuss about the materials which are generally used for manufacture of the metallic packaging materials or metal containers. Generally, the cans are made from either aluminium or steel. The steel can be chrome plated or laminated. The commonly called tin can, it is actually a misnomer. The sheet of this can have only a thin coating of tin either on one side or maybe on the both sides. Taking the different materials, the first one is aluminium. The composition of aluminium alloys for rigid containers varies according to the intended use, with up to 5% magnesium, 1.5% manganese, and traces of iron, silicon, zinc, copper, and titanium. As aluminium alloys or tempers commonly used are a fully hard material such as 3004 H19 and a softer one such as 5052 H34, where 3004 or 5052 denote the aluminium alloy sheet and H19, H34 denotes the tempering or the type of temper. The hard tempered alloy H19 allows a very thin gauge which makes the container bodies economical, and shallow drawn parts such as can ends use alloys with less ductility and medium temper of H34 for average conditions. Next material used is steel. This is a ferrous metal used in fabricating cans. It includes BS steel or a black plate, tin free steel which has thin coat of electroplated chromium, and a tin plate which has a thin coat of electroplated grade A commercially pure tin. Steel that has completed the tempering process is generally known as black plate. Traditionally, it is used for spice containers and a number of industrial packaging applications. It also forms the base of tin plate, and electroplated chromium steel. Ferrous materials are used for ends and bodies in both 2-piece and 3-piece technologies. An electrochemical passivation treatment, usually with sodium dichromate, stabilizes the surface and adds a thin film of metallic chrome or chromium to enhance the corrosion protection. Although the tin coating is only about 0.3 micrometer, it resists the corrosion not only by the protective layer of tin on its surface but also as a cathodic reaction that minimizes oxidation at any pinholes or base spots which may be found in steel plates. Tin coating also prevents the iron from being dissolved in certain beverages and food products mainly made of acidic type of products. Now we will see about can linings and lacquers. Metals used in can packaging often do not provide corrosion resistance, surface abrasion resistance, and product container compatibility. As a result, a variety of lacquer and lining materials have been developed to protect outer and inner surfaces and are also known as enamels. These are usually applied by roller or spray to flat sheet or coil and cured by oven or ultraviolet light curing process. The enamels protect the surface of can by serving as a barrier to gases, liquid and ions. Enamels generally are specified in terms of milligrams per square inch. Now we will see the applications of the metal cans. There are three major markets for metal cans: beverages like soft drinks, food and non-food comprising such products as paints, chemicals, etc. The beverage can market has been the fastest growing segment of the industry. 2-piece cans are predominant in the beverages as they are well suited to long production runs with infrequent label changes. Majority of market uses aluminium in manufacture of 2-piece beverage cans, though in some European countries still it is in use. Aluminium cans manufactured by D&I process are extensively used for pasteurized beverages such as beer and soft drinks. Beer containers carbonic gas when it is pasteurized. After sealing, the internal pressure may rise to 10 times the pressure in the food cans. The beer can therefore has to be designed to contain pressures up to 7 kg per centimeter square. Due to their lighter weight per centimeter square, aluminum cans reduce transportation cost. Remelting of aluminum cans to make aluminum slabs require only 5% of the energy used to make virgin metal from bauxite ore, so it is recyclable. Thus, the economics of recycling of aluminum cans have become quite favorable. It helps to control the cost of material and clearly favors the aluminum beverage package. Thus, the most of the beverage cans are generally made of aluminum or aluminum alloys. Then the next class is food cans. They are manufactured in greater variety of sizes and shapes than beverage cans and are generally produced in shorter production runs with frequent changeover between sizes and labels. Both 3-piece welded cans and 2-piece steel cans are commonly used. The welding process produces a high integrity 3-piece can that is lead free. Welding technology provides the flexibility to run various specifications. 2-piece cans which eliminate the side seam are well suited to short sizes but tend to use more metal in the taller sizes for food packaging cans. Shallow drawn aluminum cans are used extensively for processed food such as vegetables, certain meat products, fillets of fish and various sauces. Deeper can drawn and iron are used for vegetables in brine sauces, soups, crabs and lobsters packed in aluminum cans. The crabs and lobsters packed in aluminum cans do not require parchment lining to avoid discoloration of the product. Tomato sauce and mustard sauce are corrosive products. So the foods prepared in them, if to be packed in aluminum can, should not exceed total 3% acidity, expressed as acetic acid. Other fresh foods packed in D and R cans include meat, boned chicken, etc. A few products like roasted coffee, milk powder are canned in dry state. Heat processing and canning in such cases prevents loss of volatile and moisture pickup by hygroscopic powders. Dry packaged foods may be hermetically packed under vacuum or packed in an inert gas like nitrogen. Aluminum cans have also been developed for packaging of high sugar products. Shelf life of various food products packed in lacquered cans have been reported to be about 1 year for beer to more than 7 years for vegetables like carrots and peas. So finally, concluding the topic, there is a competition among metal, glass and plastic packaging, because nowadays most of the packages, even can type of containers, are made from plastic. So this competition will continue to be a major force in overall container industry. Metal cans have been able to maintain a large share of the market owing to technological advances permitting efficient high-speed operation and conservation of materials and energy. Recent innovations in the design and manufacture of metal packaging, especially for food products, includes large opening stay-on-tab ends for drink cans, widget to provide a foam head to beer and chilled coffee, self-heating and self-chilling type of cans. This can be used in, for example, in case of coffee. If you are having self-heating type of cans, the contents can be mixed and then it can be heated, and when open it will give you the hot coffee. The full aperture food can ends, which are easier to open, square section processed food cans for more efficient self storage, and peelable membrane ends for processed food cans. Two-piece draw and wall iron as well as two-piece draw and redraw cans made from steel with plastic extrusion coatings. The prime purpose of packaging in metal container is the physical and chemical protection of the product to be marketed. This is the major benefit which we get from the metal containers. A perfectly lacquered can is an ideal container for food with respect to all these things. This will ensure that metal will continue to have an extremely important part to play in the cost efficient packaging of foods for short or long term ambient storage conditions. The inherent strength of metal containers and the fact that they are impervious to light and moisture contribute to a high level of protection for the contained product over long shelf life periods. So friends, by now you might have understood the concept of metal packaging or tin packaging in the food industry and their applications in various aspects of food processing. Now we will switch on to the corrosion of metal packaging or metal containers in the food packaging industry.